you want to see if this works? Okay, they
Yeah,
work.
I was afraid our mic didn't work, so I was being quiet and trying to test it. All right, everyone's funneling in.
Just go.
Yeah, we're not going to cause any problems here. Let's stay on time. Welcome to our talk, The Architecture of Oban Web.
I'm Parker.
And I'm Shannon.
And we are a mom and pop software shop, as many of you probably experienced today. And we are also the people behind Oban. You can see this is the photo of us from Portugal last year.
It's not dated. We loved Lisbon last year, and we love being here this year. So COVID during lockdown for some countries, including the one we reside in, was unforgettable, and we are grateful it's becoming a distant memory. Oban Web is married to this part of time for us. It's a time where new hobbies or avid dislikes were discovered, and these are a few of ours.
Backyard chickens. This was an avid dislike of mine. We ordered 4, they sent us 8, and we kept 0.
I like them, however they were relocated.
Paying for a chicken sitter is ridiculous. We also rented a roller rink. Nobody else was using it, and we could have the whole thing. Some of us learned how to roller skate.
Some of us did. She eventually learned.
She got there.
I love fish. We ordered fish in the post.
Enough said.
It was an experience. We built a sauna in our backyard wearing swimsuits with power tools. Our neighbors probably loved it.
The instructions were in metric, if you call them instructions, because...
Well, they were in Finnish, so he said it didn't count, but we got there in the end. We lived for 38 days at Disney World.
In an Airstream, which is that silver trailer you see in the back.
Yeah. Also married to Oban Web in my mind is us having to watch Tiger King in the Airstream, which happened to us.
But more importantly, we snuck into 13 different pools at Disney World during this time.
Yeah, there's lots of pool sneaking. There was one we could not breach, and we really gave it a go.
And most importantly, hand drew all of the slides for a talk. This is from The Architecture of Oban.
While beautiful and effective, and the straight lines, I think, highlight we weren't day drinking, it's very time consuming.
Only a little day drinking. This is from the initial announcement of Oban on the Elixir forum. And so this is the screenshot of the closed web beta. It's stunning, we know.
Web was a part of Oban from the beginning. Everybody wants to see what's happening. That is a fantastic way to lure you all in.
And Oban Web start happened to coincide with the initial release of LiveView, which was 6 years ago now, believe it or not, in 2019 at ElixirConf EU. And Oban Web has been LiveView from the very beginning. There was never a single-page app React phase of Oban Web.
You should ask Chris to see his tattoo and tell him Parker sent you.
Wherever it is, ask to see it.
He's going to love it. So the original system is like 2021. It involves 2 plugins, one from Oban called Gossip and another from Web called Stats. Combined, they provide counts and information about running nodes, queues, and a lot's changed since then.
Most importantly, Oban Web is open source now, and we can reveal the once secret sauce.
Oban Web is open source now.
Thank you. Originally, Web was implemented as a few plugins in a LiveView app, as we talked about. It has evolved significantly from the early days.
Summarizing the complete structure and what we find interesting in 2 sizable applications is a bit more than what fits into our 40-minute time slot. So this isn't a bait and switch about structuring LiveView applications where we won't talk about structure at all. LiveView changes dramatically, and it has since we first built Web, and it will continue to evolve. We're here to tell you basically everything about Oban Web that we think is important, and we get to do that, not how to structure a cutting-edge LiveView app.
There are excellent tutorials and entire courses on how to do that. So go check it out. And that's all. We're out.
That's it. Thanks for being here. Bye.
No, clearly this is about something a little bit deeper. It's about the data. So how do you gather, disperse, and efficiently display data for a data-intensive, metrics-driven LiveView application?
We will cover some LiveView and plenty of Oban Web, but our focus is how web in particular collects and displays data as efficiently as possible.
And to do that, to start, we need metrics. Web uses a custom, homegrown application for gathering, sharing, and storing metrics. And why in the hell would we do that?
Well, simply put, there was no library that did what we needed. And it's unreasonable to ask users to add an extension or integrate another service just for an Oban dashboard. With our dependency should not come many more dependencies.
No new dependencies. Part of the promise of Oban is that it only needs Postgres, Elixir, and hopefully, for your sake, some distributed Erlang. So our metrics shouldn't rely on persistence in a central location. In our case, at least, pushing more ephemeral data into Postgres is a really bad idea.
Because PubSub is where it's at. All the nodes just communicate directly with each other. The resulting data store must be fully queryable at runtime with arbitrary filters and slices of time. Labels from each data source enable filtering, getting time slices. This requires something beyond standard histograms.
It's essential that we can record metrics like, say, execution time accurately in any histogram, regardless of how long they take. And so that led us to sketches, or the sketch data structure.
All right, so we're going to spend the next 20 minutes going through this. And as you can see, the sketch proof follows Cheval's proof and the special case of the Hulferding bound.
No. This is not that kind of
20
talk.
minutes.
We have no clue what this is proving. Some do. But
true.
You should ask to see Shannon's tattoo.
Oh, I have commitment issues. I don't have a tattoo. But I know there's one person in this room. Mr. Verding definitely could explain this to us all.
Seriously. Sketch data structures are designed to approximate statistical properties of a data set while consuming much less memory. Values are automatically bucketed using an estimate function instead of keeping the raw values.
And some apps have jobs that run for milliseconds, others run for hours. And we want to record them accurately without predetermined buckets. A key advantage of sketches and the gauges we use for counts is that they're fully mergeable.
So you can take any window of time from any period or from different sources, and you can combine all the values into one single coherent value. And this mergeability, helps to conserve memory as well. And that's what we call compaction.
All of us. That's what we all call it.
We can all call it compaction. So to store data points from an unknown number of queues and workers and nodes, we need an efficient storage system that can be compacted. Over time, the fine-grained data needs to be merged into bigger windows of time to save on memory. So for the last minute or two, you save 1 second resolution. For the last couple of hours, you save 1 minute resolution. And finally, this has to be a single standalone package.
Because worker-only nodes that don't run a web server, they need to collect data too. It should drop into any node that's running Oban. Thus, by Oban Met. I don't know if any of you have, judging by the stars, very few have, but this hidden and vastly important package, open sourced with web, is crucial to how it works. So, I'm both very close and highly biased, and in this group, I'd like to tell you, it is the best code Parker has ever written. So go check it out for yourself.
Give it some love.
No configuration is necessary, and Oban Met will start automatically in a typical application.
Each Oban instance has an associated metrics supervisor, which is initialized automatically through telemetry magic. So here's the supervision tree that kicks off. Each metrics instance is a supervisor itself with dedicated processes for tracking cron, examining job counts, runtime execution stats, all that.
Yeah, there's more on that.
And that's it for metrics. So we're moving on to Oban Web. Starting from the outside with the application itself. And here it is. This is a recorded demo because we learned our lesson last year.
Just do it. Everybody loves a live demo. Even when it goes wrong, it's right.
The demo gods love you. No, they don't.
Shame.
Web relies on the database for job data, and Met for the metrics, and Oban itself for operations like canceling jobs, retrying jobs, scaling queues, that kind of thing. And this is the high-level 50,000, 30,000, I don't know how many feet, view of the entire web application.
There are no feet. You're in Europe.
It's a good call. It's the essentials.
It is the essentials. It's routing on the page, mounting, data passing.
So web doesn't have access to your app's asset pipeline.
We also don't have any access to your data. So if you ask me for us for a SOC 2, and you get an email back saying, we don't have SOC 2, it's because we don't have your data, ever.
No. So any styling or JavaScript that you need in web, it has to bring in. So everything is bundled at compile time and embedded into a module. It's then injected into the layout as just a raw value,
which the dashboard loads when you navigate to the URL. The way it interfaces with the outside application is via the Oban router, which mounts to your application's router. The Oban Web router mounts through a single Oban dashboard macro.
So after massaging the macro options to prevent really mysterious scoping issues, it mounts web as a single live session into the host app. The exact startup order of the Phoenix endpoint is out of our control. If Oban was started first and Phoenix was started second, then you're going to get weird crashes.
And since we don't control how you do things, to compensate, we control how we do things. And since we don't know which starts first, the dashboard relies on telemetry events to wait for Oban and Met to start. Because there are telemetry events for startup and a central registry, we have ensured you have the ability to switch between multiple Oban instances without mounting multiple dashboards.
Like the olden days, those 2023 days.
So long ago.
There's only one live view, that's the dashboard, and then there are a bunch of pages within that. Those adhere to a common behavior, the page behavior, and that's what defines the jobs, the queues, the crons, eventually, and other structures. So that way, the pages can share standard parameter handling and refresh, updating, that kind of thing. And so the dashboard starts a central timer when it mounts, and that's what triggers a page's handle refresh. So refreshing also pauses when you leave the page, but the metrics keep updating in the background because they're unrelated. And so they do that through PubSub, and the PubSub is essential to web functionality. So with disconnected or isolated nodes, the dashboard doesn't have any data, and frankly, it looks broken.
And that is our #1 web support question. None of my queues are showing up. Why? Well, to help, web routinely checks the connection status through the notifier, then shows a connectivity warning on the dashboard when the node isn't connected. There's a bit of a Byzantine general situation that happens here where it's a single node where it can't tell it's the only node, but it's helpful as an indicator, so I say this a lot. What is a Byzantine general situation? He's my decoder often.
Byzantine generals, you have two armies. They're separated by a big hill. They try to send messages from one army to the other, but you don't know if it got there. Were they killed? Did they never make it? You can't tell. So it looks like you're isolated, but you don't know if you really are.
I wanted to reenact this in person, and he had to rein me in. So moving beyond the application into components of the page and how they interact with data.
You can select jobs for bulk operations, as you can see here. So canceling, retrying, bulk operations. You can also change the sort order, attempts, time, worker.
All the typical things you can do with the table. It's pretty typish.
It's a table, yeah.
But this is the way that the data flows through the page and to the table. Queries run directly on the jobs table in the database, and they are slightly augmented from data by metrics. And that presents a challenge. How to fetch as little data as possible to list jobs.
So data fetching and the deserialization through the query module adds time. So Oban retains errors and timing info, and if you have pro, recorded data, and that adds up a lot. So they're used for observability and auditing, but you don't have to fetch them when they're not shown.
No, because it's wasteful.
So this is a somewhat selective list of fields that reduces the amount of data fetched. So for instance, errors and tags are omitted. And meta used to be omitted, but now it's not because of features.
All right, on to challenge number 2.
So how do you query and paginate an Oban jobs table with potentially millions and millions of rows?
Querying with custom ordering and limits is a serious performance concern for a query that runs every 1 second for every person viewing the dashboard. How do you avoid that? Notice this part of the pipeline that built the query we just showed earlier. It limits the total depth of jobs that the query looks at with an extremely fast subquery. This is a threshold query.
So the threshold query takes the most recent ID and subtracts a fixed number from it. Then that's used as a condition in a where clause to limit the total depth without using order or limit. And this way, you don't have to scan and filter the entire table before applying the limit.
For someone who asked us earlier, that is the secret sauce. The threshold is 100,000 jobs by default across all states. This can make it confusing for people when they search for jobs that they know are in the database and yet nothing shows up.
Well, we address that by making it customizable with a resolver callback. So the resolver module is a way to customize the way Oban Web behaves. In this example, it's implementing a jobs query limit so that the available and completed jobs have a shorter limit, and everything else beyond that is just infinite.
Challenge number 3.
Sure.
How to indicate which jobs are really running and which are orphans.
Some information about jobs is available in the database, like when did it start, how long has it been running, which node is it running on, but whether or not that node is actually still alive, that's not in there. So how can you tell when a node has orphaned a job, meaning it's just not actually there, the node is shut down, but it looks like it's executing?
The jobs table uses check data to get a set of producer UUIDs. And we'll chat more about checks in a moment because I air quoted them.
Yes, she keeps using checks in air quotes because it means checkpoints, but that's not a standard term.
I write it like that to him because when we wrote checkpoints, he felt it was too long and it didn't match the other parts of our code, and visually it disturbed him, so it had to be shortened to checks.
We all have our issues.
The UUID is compared against the jobs attempted by field to see whether the node that attempted the job is still running. The data from Oban Met is used everywhere. Oban Met, PubSub, it's just the beginning. It also drives the queues table. The queues table is completely different as far as the data goes. It's still just a table underneath. There isn't a database to pull, so the table is entirely derived from the checks and counts shared by Met. It supports bulk actions for pausing, resuming, sorting, stopping queues, all of that.
And then the queues page fetches the data through a standardized query module, just like the jobs table. But how do you display real-time queue data without a central database? So queues are supervised processes spread across all of your app's nodes. It might run on one node, but not on another node, and they can be started and stopped dynamically. And data about those queues must be sent from every node. So each Met instance runs an examiner process, and that periodically scrapes information from all the running queues. So using Oban's registry, the examiner can find all the queues and then extract checks from them in parallel as safely as possible.
And the data that comes back is exactly what the check queue function in Oban would get. The scraped data is then shared with other instances via PubSub. And like I said, you hear us say that a lot, but this is a common pattern for metric processes. All that check data can then be aggregated, essentially grouped by queue on the web node. Notice that the latest counts for available and executing states are pulled in as well.
That aggregate data, that's what the queues table displays. So the count of individual queues becomes the number of nodes, the limits become a range of limits, etc. And pausing, resuming, scaling, those kinds of operations on a queue, that's all done through PubSub signals. So every node can respond to an event. Web subscribes to the same events, and then we'll update the dashboard accordingly. So in the queue details page, when you change the limits and hit scale, it's broadcasting that signal to all the other nodes, telling them to scale.
And this is exactly the same as calling scale queue from Oban, and that's just the button. The signals can be scoped to a single node, so you can scale queues separately, and this comes in handy for triaging, I call them fire nodes, but nodes on fire, and dialing them down.
Nobody likes a node on fire. It's bad.
Node on fire is a bad band name. This next component that makes a heavy use of checks and counts is the jobs sidebar.
As you can see, the counts are front and center for the sidebar. So they show the total number of jobs in each state, and then they also mix into the nodes and queues for executing and available. And all those links are all clickable as filters later. So the checks flow through the queries table into the sidebar, where they're aggregated and merged with the counts. The latest counts are pulled from metrics, grouped by state.
Which sounds really easy, I'm sure. How to get updated, accurate counts by state and queue without killing the database.
It's pretty hard, as you guessed from that particular setup.
So getting counts with a one-off query is fine. But when you need to run those counts every 1 second, it becomes trickier. The Met instance on every node runs a reporter process that's responsible for taking counts from the Oban jobs table, and only one reporter on the leader node actually does the counting to prevent duplicate work, because the count query itself is the problem.
Because every time you run select count, Postgres has to scan the entire table to count all the rows. Even with an index, it still needs to check each row for visibility because of the way it does concurrency. And we're focusing on Postgres instead of MySQL or SQLite because it's better, except in this case. So as you may guess, this counting is inefficient and expensive with larger tables.
The larger the table shouldn't always mean the slower the count. Without introducing separate tables to track counts, which has its own issues, the best way to avoid that expense is to estimate and not count. Or instead of it, just instead estimate. This is a custom Postgres function defined in Met to get an estimate with state and queue filters. So counts for smaller states are done with a regular count, and larger states are estimated.
This is a trade-off that preserves system resources at the expense of accuracy. So the completed states, as you can see here, is well over the threshold. It's 780,000. So the count is estimated, plus it's rounded anyway in the display, and you wouldn't know any better.
And it seems like a minor detail, but the impact on someone else's system is massive.
We have no control over what database somebody runs this on, or the size of it, or any of that. And it took years, believe it or not, to get slow query reports and finally get to this point. So the first count Met runs is always full. After that, any state that has fewer than 50,000 jobs will use the faster estimate function. That can be a little bit confusing for people who do bulk inserts of hundreds of thousands of jobs. So the estimate limit can be configured globally or for a particular instance. So like here, it's bumped up to 200,000. We had to.
it's not really a show, like a shameless pro plug, because we're here and we love being here. We just had to tell you that with pro, globally limited, and rate limited queues are indicated in the sidebar. Still fully driven by checks. So switching away from the checks and counts for a bit, we'll go into the filters. Colorful, active, the drama, so dramatic. You can see that it's auto-suggesting in the combo box there, pulling directly from the database. We're not adding other indexes. You just drop it in, and it works.
And it's so purple.
You really didn't like the purple.
Yeah, it's a stretch.
Well, I won one. Purple. The filtered data flow looks fairly simple, with data pulling through the jobs query and from the only jobs table. But it's complected by a few things.
Got the complected. All right.
I did it.
Note the completer link on the bottom to the search component. That's the first challenge.
So.
Not that challenge.
Yes.
Better.
How to make a keyboard-driven combo box.
So making a smooth, fluid, buttery combo box in LiveView is surprisingly horribly difficult. Has anybody else tried? No? There you go. So this is a slight digression because it's really not about the data, but it's just such a pain in the ass we had to share. So
oh, that's so spicy.
Digging a little deeper. As you type, the filter input triggers events in a completer hook. Then the hook listens for keys like tab or enter, which it then uses to coordinate suggestions and completions.
Okay, there was a JavaScript slide here.
Not anymore. It's gone.
You are awful. He does feel so spicy about it. Is it really gone?
Yeah, I could not stand. All right.
Okay, he removed the JavaScript slide. Again, I lost another one. So when the input changes during typing, it hits a standard handle event and starts an async suggestion. The suggestion query starts in a task with a fixed timeout. This predates start async, which doesn't support this yield technique as far as we know, right? It does differentiate a bit and maybe give you a little bit of color.
And so the task passes the current input buffer through to the suggest function, which is the next challenge. So how do you query for suggestions efficiently? So querying the entire jobs table for a worker, queues, nodes, to say a few, would be terribly slow. But there are a few techniques at play to speed it up. First, again, we're using threshold queries, as we talked about earlier, but this time applied to suggestions. Second, we cache recent values in memory to prevent touching the database again for the next query. And then you can match on the input in memory rather than hitting the database for the additional queries. So that caching just insulates it. So instead of every time you type, go into the database, you're just doing it straight out of memory.
Because the alternative is a full text search, which needs specialized indexes, and it still isn't, it's just nearly not as fast.
You have to go to the database, and as we said before, no new indexes. The other benefit is it can use gyro distance to sort by similarity in a typo-tolerant way. And then it can skim the top matches, and it favors anything that starts with the exact same letters to bubble those up to the top.
Maybe you saw this one coming. We thought you would see this one coming, but just like query thresholds, suggestion thresholds, they're customizable too.
So for example, to look back at fewer args and meta, because those queries can be more expensive, but then expand to 20,000 for everything else, you would implement the hint query limit.
Once you have a suggestion and choose a value to filter by, how do you keep that efficient? Especially for JSON fields like args or meta, where you need to filter by nested paths. The same filters need to work in SQLite, MySQL, Postgres, and any supported database is what we mean. JSON path queries aren't consistent between databases.
Values are type sensitive, so sometimes you want to search for an ID, other times you might want to search for text. So it takes a little bit of extra typecasting to match intuitively. But it still stays fast and queryous, even on large tables, because the dot paths are converted into maps so that no matter how deep the path chain, an efficient query is always built from the nested maps and the very important containment operator. So the containment operator, or curious bird face, as we like to say, is one of very few JSON operators in Postgres that works for indexes on generic queries.
This is an important optimization for filters on args and meta. It's not nearly as fast as a custom index. So we're going to move out of the database and back into metrics. But last but not least, our personal favorite, the reason we had to build Met, the charts.
Definite favorite.
It's the drama, isn't it? It displays a variety of real-time metrics from execution counts to queue wait time. All of those metrics can be sliced into different time units so you can see more history. And for sketch-based metrics, you can change percentiles. All in one flexible, dramatic, colorful chart. It's so fun to look at. I think it is.
I agree. The chart component pulls exclusively from metrics and then pushes those up to a charts.js instance, which renders a canvas. So it's really lightweight, and it's what makes drawing all the various types actually really flexible. This is a place where LiveView and JavaScript interact is really good.
So, how to gather real-time accurate values for job execution and queue times from all nodes.
You need fresh timing and counts recorded on every node to have remotely meaningful charts. So where do you record those values?
With a listener module in Oban Met. It listens to stop and execution telemetry events for every job executed on every node. If you've ever instrumented Oban before, or hooked up a manual error handler, which I'm sure everybody has, you know that the telemetry events carry all the metadata that's needed.
And an event handler grabs the execution time, the queue wait time, whatever else it needs, and then it bumps the execution count for each job. And they're recorded as raw values at the current timestamp in an ets table.
Well, for now.
So it's not shown here, but the table is actually a duplicate bag because we just want to get it in there. We don't care whether they're unique. We want to insert as fast as possible and then deal with all the data later.
There's no such thing as atomic fetching from an ets table. So when it's time to share metrics with the other nodes, it uses timestamps to selectively delete from the table.
In this case, anything before timestamp 4 is popped out safely. And that's done with a combination of select and select delete to safely pull metrics out of the table. It's the safest, fastest multi-process pattern we've discovered for this kind of operation, which we do a lot.
Yeah, who doesn't love writing super obtuse match specs?
So efficient and
so ugly.
So ugly. At this point, the raw numeric values are converted into gauges or sketches, depending on the metric type as well.
Right. So, how do we aggregate metrics for filtering and slicing in memory?
The values from all those listeners and reporters, as you might remember from earlier, need to be in a central location to read from.
It's yet another job for PubSub, right?
It is. The recorder process aggregates data from the reporter and listener processes in another ets table.
There's a lot of ets action going on in Met.
Yes.
But notice that the values are stored with labels and a min-max time range in the recorders table.
The time range allows for queries to pull any values that overlap within a particular time period. And then the labels, which are stored as a map, make it possible to do all of the filtering actually directly in the ets table with another gorgeous match spec.
And from there, because the gauges and sketches are mergeable, they're reduced to a single value. And that's the data point used by charts. The label filtering makes it possible to filter the charts along with jobs using nodes, queues, and workers.
And you can tell that a filter is applied by the violet dot. Hovering will tell you which ones are actually applied.
And it's purple.
It is. There's plenty more to the way that charts work, from the way that it interpolates missing data points, to storing options, to pushing events up to the charts, but that was already a lot.
There was a lot, and we like talking about all of it. So if we've skipped some major features or you have questions, please feel free to seek us out. You know where to find us for a limited time in person, however, also online. It's difficult to summarize the key points of these two applications, but we're going to give it a go.
So here are the 5 core takeaways from our little group chat. Isolate from the parent application, number 1, and avoid additional dependencies.
It should not come with many more dependencies. Optimize for laziness in every query. Blindly cache aggressively and work in memory. Strategically cache aggressively and work in memory.
Strategically is better, yes.
Yes. And telemetry and ETS are your besties.
Remember, it's all about gathering, querying, and displaying data efficiently in the LiveView app.
So if you haven't already, we hope you'll check out Web and Met. Please go look at Met. Contribute to them if you'd like. They need some love, and they're open source. And we're so pleased to be here and part of this vibrant, beautiful community.
And remember, they're supported by Open Pro, so thank you all.
Dziękuję.